Hi, welcome back to Earth Materials. Today we're going to discuss phase diagrams. I will first discuss solid solutions, processes of Exsolution, and I'll explain what that is, mineral stability fields, and then I'll talk about binary loops and fractional crystallization. I will briefly mention Eutectics, but I won't spend very much time on it. And so at the end of this, I hope students will be able to explain the concept of solid solution and give some examples of minerals that might have a lot of solid solution versus very limited solid solution. Look at a simple phase diagram for alkali feldspars to explain how their compositions might evolve during cooling, to talk about mineral stability fields as a function of pressure and temperature, and then to say something about how mineral and melt compositions evolve for igneous systems. So first, let's talk about solid solutions and Exsolution. Solid solution is the complete mixing of at least two cations in a mineral. So one of the examples that we use a lot in geology is olivine. Olivine has two octahedral sites that mix iron and magnesium pretty much randomly on it. We call this simple substitution. We can express it as MgFe minus 1. So if you add magnesium, you can subtract iron from it. This is how metamorphic petrologists describe substitutions. This is called an exchange vector. You're exchanging magnesium for iron. Plagioclase has a coupled solid solution. So a lot of times we talk about how sodium and calcium mix on a large site that is in the feldspar, but to charge balance this, silicon and aluminum also have to mix in a tetrahedral site. So the substitution is sodium plus silicon exchanges for calcium plus aluminum. So this is the way we would write that exchange vector. And the degree to which cations mix is very strongly temperature dependent. So olivine has strong solid solution behavior over almost all temperatures. Plagioclase and many other minerals have strong solid solution at high temperature, but they can have more limited solid solution at low temperature. And just to give you a sense, this is a very magnesium-rich olivine. This is a phaolite, iron end member olivine. Here's albite, pure sodium feldspar, and here is anorthite, pure calcium feldspar. These are the end members that mix in feldspars, plagioclase feldspars. These are the end members that mix in olivine. However, as I mentioned, there are some exchanges that do not mix very readily, and we can look at some other exchanges, calcium, magnesium, calcium, iron, and iron, magnesium. This one does show complete solid solution in most systems. Here I'm showing ternary composition diagrams. This is for the carbonates, calcium carbonate, calcite, magnesite, siderite. And we can see in magnesite siderite, there's complete solid solution. So this dark field represents the field of mineral stability for magnesium iron solid solutions, for magnesium iron carbonates. This is dolomite, so it's halfway or about halfway between magnesite and calcite. It has extensive solid solution with respect to iron and magnesium. This composition here is called anchorite. Calcite sits up here, and this purple field is actually a field where no carbonates are stable. If you have a bulk composition that sits in this region, it would consist of three different carbonates: anchorite, calcite, and siderite. Okay, so what we see is there's extensive solid solution in the iron-magnesium system. There's very limited solid solution between calcium and magnesium end members. So there's a gap here, compositional gap between calcite and dolomite. And there's another compositional gap between dolomite and magnesite. Similarly, over here we see a compositional gap between calcite and siderite. This same kind of behavior occurs in many, many other minerals. So here, for example, are pyroxenes. This is called the pyroxene quadrilateral, enstatite, ferrocylite, Hedenbergite, CaFe, Si2O6, and diopside, CaMg, Si2O6. There's complete solid solution between diopside and Hedenbergite. That forms the mineral augite. And there's complete solid solution between enstatite and ferrocylite. This forms the orthopyroxenes, but in between there's a compositional gap. So there's a gap in pyroxene composition between diopside and enstatite. they separate into two different phases if you have a composition that's in the middle. There's another compositional gap between Hedenbergite and ferrosilicate. There's a little more solid solution here, but there's still this composition gap. So Hedenbergite would coexist with ferrosilicate if you had a bulk composition that was sitting right here. Okay, quick question. Andesite ferrosilicate show complete solid solution. Which of the following mineral end members would you expect to show the same complete solid solution behavior? And the answer is olivine. We talked about this before, but this is the mineral system. These are the two end members that show exchange along magnesium and iron end members. These other minerals either have a different kind of exchange to relate them, or they don't have any exchange. Okay, amphiboles behave in exactly the same way. Iron and magnesium is nearly ideal. Calcium magnesium is very non-ideal, so that separates out calcic amphiboles from iron magnesium amphiboles. And iron and calcium are pretty non-ideal. They tend to separate calcium and iron-rich minerals, but not so strongly as calcium and magnesium. Okay, let's look at a different set of exchanges. These are the alkali ions, calcium, sodium, and potassium. These are important for micas and zeolites and feldspars and several other minerals. Now, calcium is a divalent cation. Sodium and potassium are monovalent. So you have to do something else to balance charges to mix calcium with sodium and potassium. And the answer is that you mix in aluminum and silicon. So calcium plus aluminum substitute for sodium silicon or potassium silicon. If we look at a ternary composition diagram for the feldspars, we find that at moderate temperatures, there's complete solid solution between the anorthite calcium and albite sodium end members. And there's a lot of solid solution between potassium feldspars and sodium feldspars, but there is still this composition gap that occurs at intermediate to lower temperatures. Micas behave pretty much the same way. There's a fair amount of solid solution between the calcium end member margarite and the sodium end member paragonite. Not as extensive as we see in the feldspars, but there is fairly extensive solid solution. And we see kind of the same thing for potassium end member micas, sodium end member micas, that there is moderate solid solution, but there's also a composition gap. And we also see there's no solid solution between the calcium end member mica and the potassium end member mica, just as we see there's very little solid solution, almost no solid solution, between calcium feldspar and potassium feldspar. So what does this mean? Potassium and sodium exchanges show extensive solid solution at high temperature, not very much at low temperature. Potassium-calcium is very non-ideal. We see very little solid solution between potassium and calcium end members, and we see extensive solid solution between sodium and calcium end members, at least at high temperature, not so much at low temperature. This leads to the concept of Exsolution and a first phase diagram that we're going to talk about. Now, Exsolution is the separation of chemically distinct minerals, two minerals that have different compositions, from what was originally a single chemically homogeneous material. The type of phase diagram that describes this is called a solvus, and it simply means that in a solvus there are two chemically distinct minerals for a given composition rather than a single homogeneous material. Now, a solvus presupposes that there's some kind of similarity in lattice or physical structure. So we can talk about feldspar-feldspar solvi, or pyroxene-pyroxene solvi, or amphibole-amphibole solvi, but we really can't talk about a solvus between two completely different minerals. We wouldn't talk about a mica olivine solvus, a mica pyroxene solvus, or anything like that. Okay, so let's look at the feldspar composition diagram. Here's our composition diagram. This is shifted around. So now potassium feldspar is at the top, calcium feldspar on the right, sodium feldspar on the left. Now, if we had an alkali feldspar with a composition that was, well, let's say about 60% albite, it would be completely stable at a temperature above about 700 degrees. So here's the solid solution behavior, this boundary at 750 degrees. So you could have a homogeneous feldspar anywhere within this region that is down or to the left of this stippled region. So we could have a stable feldspar at 750 degrees that has this composition. If we cool it slowly enough so that it equilibrates along the solvus, I'll show you what that means, at 650 degrees it would separate into two different feldspars. There would be one feldspar that has this composition and another feldspar with this composition. That is, there would be two coexisting feldspars, not a single homogeneous feldspar. And so that's what I'm trying to say here. If you have this composition, let's say it's about 60% albite, it would be stable at high temperature and moderately high temperature, but not at low temperature. The way that we show this kind of behavior is with a temperature versus composition phase diagram. A lot of times we just call these TX diagrams. And TX diagrams have boundaries, this is the solvus, that separates two different fields. At high temperature, we have a single phase field, so that means that any composition up here will be a homogeneous feldspar. And in the middle, inside the solvus, we have what's called a two-phase field. In the two-phase field, if you have a composition that fell in here, so for example, you had a high-temperature feldspar that cooled into this region, the feldspar would try to separate out into two different feldspars. It would separate out into an albite-rich feldspar and into a potassium-rich feldspar. Now, it's important that near end member composition feldspars might never hit this solvus. So if we have a very high sodium feldspar, nearly end member albite, as it cools off, it will never hit the solvus. So it will always stay in the one phase field and it will always be compositionally homogeneous. You won't separate to two different phases. And the same is true for a near end member potassium feldspar. If it has very little sodium, as it cools off, it never hits the solvus, so it maintains its composition. It doesn't separate into two different feldspars. The compositions of the feldspars track this solvus. So let's just imagine that you take this dot, you cool it slowly, it hits the solvus, you enter the two-phase field. When you get to this temperature, whatever that is, 700 degrees say, you will have a potassium-rich feldspar of this composition and a sodium-rich feldspar of this composition. As the temperature cools, if it continues to separate, then the composition of the potassium-rich feldspar will shift to this composition. The composition of the sodium-rich feldspar will shift to this composition. And as we get to lower and lower temperatures, the potassium-rich feldspar will get more potassium-rich and the sodium-rich feldspar will get more sodium-rich. That is, the compositions of the feldspars track the boundaries on this solvus. The amounts of the two different phases that are present are given by the lever rule. And all that the lever rule here, this is the way I remember it. The lever rule says it's the proportions are the ratio of the short arm, so here B, to the total length, A plus B. So one of these has a proportion of B to A plus B, and the other one has a proportion of A to A plus B. And I can never remember this. So all I know is I know that there are these two ratios. One is B to the total length, the other is A to the total length. And then I just see, well, is my composition closer to the sodium-rich side or is it closer to the potassium-rich side? Well, if it's closer to the sodium-rich side, then the sodium-rich side must be the ratio B to the total length because that's the bigger proportion. And I know if my composition is closer to this boundary, I have to have more of it. Okay, so in some ways I kind of remember the lever rule, but not really. I just remember what these ratios are and then back out which proportion has to correspond to which phase. Okay, so just a little thought experiment here. For this diagram above, for this blue hexagon, which component, A or B, would be the most abundant? And the answer is B, and that's because the hexagon is closer to B, so there would be more of it. So in this case, the proportion of B would have to be this length divided by the total length. The proportion of A would have to be this length divided by the total length. So now we can go up here again. Here's our circle. If we cool our circle down into the two-phase field, so it separates out into a sodium-rich and potassium-rich feldspar, which would be most abundant? And the answer is it would be the albite-rich feldspar, because this composition is closer to the albite-rich side of the solvus. There are lots of solvi in lots of different mineral systems. Plagioclase has multiple solvi at low temperature. It's possible to buy labradorite, which is a type of feldspar that has this sort of Schiller effect. You get these blue and green colors when you reflect light off of it in a particular direction. I don't remember off the top of my head which solvus it is. It's either the Bogild or the Huttenlocher gap, but intermediate feldspars up here, when they cool, they hit one of these gaps. They exsolve two different feldspars. One's more calcic, the other one is more sodic. And the fine intergrowth of these two feldspars diffracts the light and allows you to see these blue and green colors. Alkali micas, paragonite and muscovite, sodium and potassium micas, also separate into two different crystals. So here's paragonite, this dark gray material in this backscatter electron image. Phengite is a type of potassium mica. It's like muscovite with a little extra magnesium and silicon in it. So this is coexisting potassium and sodium mica. And here are two salts. Here's sylvite, potassium chloride, and halite, sodium chloride, showing again the separation of these two salts along the sodium-potassium exchange vector. Okay, thought question. Which of the following minerals, when cooled slowly, might exsolve to produce two distinct crystalline phases? So, in other words, if you took one of these compositions, compositionally intermediate olivine, compositionally extreme olivine, which of these would hit a solvus and separate into two different materials? And the answer is a compositionally intermediate feldspar. So if we go back, let's just run back up here. If we have a compositionally intermediate feldspar, it will enter the two-phase field during cooling. If we had a compositionally extreme feldspar, it would not. Okay, so I hope at this point you have a better sense of what solid solutions are, and maybe have a couple examples of minerals that have extensive versus limited solid solution, and then be able to say something about feldspar compositions and how they would evolve during cooling, maybe extrapolate to other systems that also have solvi. Okay, let's spend a little time talking about mineral assemblage stability. There are many other types of phase diagrams. A really common one that we see in metamorphic petrology is a pressure versus temperature diagram that has boundaries that separate the stability fields of different minerals or mineral assemblages. So one of the most common ones that we talk about is the aluminosilicate phase diagram. The aluminosilicates have the same composition, Al2SiO5. So this field over here, kyanite is stable. In this field, sillimanite is stable. Sillimanite are these little needles here. And in this field, low pressure andalusite is stable. This is a big crystal of andalusite with a beautiful chiastolite cross. It does get more complicated if you add other chemical components, but for this end member composition, this is the phase diagram that describes the stability fields of these three phases. Now, if you start adding other components to the system, then there can be other minerals that are stable at different pressure temperature conditions. So if you have quartz in a system, there is the mineral pyrophyllite. Pyrophyllite has this composition. You can see it's almost like aluminosilicate, Al2SiO4, except it's got some extra silicon in it and it's hydrous. Well, if you add quartz and water to a rock, kyanite and andalusite are no longer stable in this PT region. Instead, the mineral pyrophyllite is stable. So the boundaries between these fields correspond to different reactions. This is the reaction kyanite goes to sillimanite. This is the reaction andalusite goes to sillimanite. This is the reaction kyanite goes to andalusite. And this is the reaction pyrophyllite goes to kyanite plus quartz plus water. And this part of the reaction down here is pyrophyllite goes to andalusite plus quartz plus water. This set of reactions that link into these little nodes and reactions emanate out from here, this is called a petrogenetic grid. And basically a way a petrogenetic grid is for a particular bulk rock composition, something that has a lot of aluminum and silicon and water, we simply look to see what the stable assemblage is in this region. In this case, it's pyrophyllite plus quartz. And we look to see what the stable assemblage is here. Kyanite plus quartz plus water. Here it would be sillimanite plus quartz plus water, and here it would be andalusite plus quartz plus water. Now, why do we care about this? Well, it turns out that the stability fields of these different minerals can help us understand the pressures and temperatures at which rocks form. So, for example, let's imagine that you knew independently that the temperature in a rock was 560 degrees. We have many different thermometers for determining temperatures in rocks. So let's just imagine we apply one of those to a rock and we find that the temperature is 560 degrees. How do we know what the pressure is? Well, if you see a transition between kyanite and sillimanite at that transition, then you know you have to be right at this point on the boundary, which turns out to be around 5 kilobars. 5 kilobars would be somewhere between 15 and 20 kilometers depth in the crust. And so that's why we care about these petrogenetic grids. It's because it allows us to learn something about the conditions under which metamorphic rocks form. Typically, that's how they're applied. So now if you had, let's say, a pressure temperature diagram that had a petrogenetic grid with all the fields labeled, and I said something like, for this pressure and temperature, what is the stable mineral assemblage? You could go to the petrogenetic grid and say, oh, here's my assemblage for this particular field. Or vice versa. If I give you a mineral assemblage and a petrogenetic grid, could you go and find it on the pressure temperature diagram and say something about the pressure and temperature of mineral equilibration? Okay, the last thing I want to talk about is getting back to igneous systems to talk about binary loops and fractional crystallization. So a binary loop has this kind of configuration. It's again a TX diagram. The upper field is a single phase region. The loop here is a two-phase region. And the lower field here is a one-phase field again. Now, most of these that we talk about are melting systems. So the one-phase field down here is a solid. The two-phase field here is solid plus liquid. And the one-phase field up here is liquid. So this one is for olivine, forsterite end member on this part of the diagram, phaolite end member here. So these are olivine compositions along here. And this is temperature. This is the melting point of pure forsterite above 1800 degrees. This is the melting point of pure phaolite at about 1200 degrees. And what this shows is that if I took an olivine of, say, 50% phaolite, 50% forsterite, if I raise the temperature to, let's say, 1600 degrees, it would contain coexisting liquid and olivine. This olivine SS means olivine solid solution. And how do we figure out the compositions and proportions of these phases? Well, we do it in exactly the same way that we did with the solvus. We draw a line across here, we balance it for that composition, and we determine the composition here. This is the composition of the liquid because it's up against the liquid field. This is the composition of the solid because it's up against the solid field. And then we use the lever rule to figure out the proportions. This line, because it tracks out liquid composition, is called the liquidus. This line, because it tracks out the solid composition, is called the solidus. And there are many different binary diagrams. Olivine is an important one. Plagioclase is another one. So here we have liquid as the one-phase field at high temperature. Here we have solid plagioclase as the one-phase field at low temperature. And in between, we have this binary loop of coexisting liquid and plagioclase. There are some really interesting things about this. So if you take a liquid of this composition, corresponds to 70% anorthite, and you cool it slowly, the liquid will just get colder and colder and colder until it hits the two-phase field. And at that point, it starts to form a crystal of plagioclase. But look at the composition of the plagioclase. It's not the same as the liquid. The first plagioclase that forms has a composition that's much more anorthitic. It's at least AN90, 90% anorthite. And as this liquid cools, now the liquid follows this compositional line, the solid follows this compositional line, so the liquid gets more and more and more sodium rich. The feldspar also gets more and more and more sodium rich until we eventually get to this temperature, whatever this is, 1390 degrees, whatever. The very last liquid to coexist with this plagioclase has this composition, AN35, something like that. And the feldspar now has a composition equivalent to the original bulk composition around AN70. And if we keep cooling it further, that feldspar maintains its composition. So let's take the reverse example. Let's imagine I heat olivine with this composition, 60% phaolite, and I heat it up until it hits the two-phase field. What composition liquid do I produce first? More iron-rich, more magnesium-rich, or the same composition? And the answer is it's more phaolite-rich. Okay, this is a really important concept. If I take a rock that has some iron-magnesium composition and I heat it up, the liquid that I produce is more iron-rich. Okay, this is why basalts have more iron in them than the mantle that melted to produce them. Now let's imagine we do the reverse. Let's say we have a liquid that has 60% phaolite component and we cool it off. What composition olivine is the first one to crystallize? And the answer is it's the more magnesium rich. And so again, if we take a basaltic liquid and we crystallize out some olivine from it, the olivine is always more magnesium rich. Okay, so now let's imagine we start out with a liquid at this temperature, we cool it, hits two-phase field, goes into this field, keeps crystallizing olivine from the liquid till we get to this point, 1500 degrees. Now, here's the question. What composition olivine is going to be stable at 1500 degrees? Is it going to be more magnesium rich? Is it going to be the same composition as the liquid, 60%? Or is it going to be more iron rich? And the answer is it's going to be more magnesium rich. It's going to have this composition over here. Remember, this is the solidus. This is what describes the composition of the solid in the two-phase field. And now last, if I cool this liquid to 1500 degrees, let's not worry about compositions. How much of each phase would you have? At this temperature, would you have more olivine or would you have more liquid? And the answer is you would have 40% olivine, 60% melt. Why is that? It's because this arm is longer than this arm. So in other words, this composition is farther from the solidus than it is from the liquidus. So there has to be less of the solid than there is of the liquid. So at this point, I hope you'd be able to predict how mineral and melt compositions will evolve along binary loops. It really does require more practice with examples, and so normally I have a problem set that allows students to have some practice with calculating compositions and calculating proportions. Last thing I want to talk about just very briefly are eutectics. Eutectics occur when we're looking at liquid-solid systems when there are two solids that have no solid solution between them. So here we have albite. Here we have a silica polymorph. At high temperature, it's tridymite. At really high temperature, it's cristobalite. At low temperature, it's quartz. But there's no solid solution between albite and a silica polymorph. If you had a composition that was intermediate, at this temperature or lower, there would be two solid phases present, no solid solution between them. In some ways, there are some similarities to the binary loop that we talked about before. Here at high temperature, we have a single phase field, which is just liquid. At lower temperature, we hit these curves, and in these fields, we have two phases present. In this region, it would be high temperature silica polymorph cristobalite plus liquid. Here, it would be high temperature polymorph tridymite plus liquid. In this field, it would be albite plus liquid. And what's important about a eutectic is that these curves converge to a single point here. This is the eutectic. And I don't want to get into all of the details of how we trace out compositions and proportions of phases and all that kind of thing. We can learn this in an igneous petrology class. But the important point here is that this eutectic composition tends to limit the kinds of liquid compositions that we see on Earth. So if you have a rock that has variable proportions of albite and tridymite, what you find is that if you start to melt it, you produce a liquid of this composition. Doesn't matter if you start with a solid over here or a solid over here, you always produce this liquid composition. Now, why is that important? Well, it turns out that granites and basalts tend to form at eutectics. So if I take a peridotite, it doesn't really matter what the proportions of clinopyroxene, orthopyroxene, olivine, and spinel might be. I could have something that's very olivine rich or very olivine poor. I tend to produce a basalt with a pretty similar composition because the basalt forms on a eutectic. And the same is true for granitic rocks. If I take a quartzo-feldspathic rock, it doesn't matter how much potassium feldspar versus plagioclase feldspar versus quartz is in it. Regardless of the proportions, if I start to melt it, I tend to produce a composition that's right at the eutectic. This is why basalts have such similar compositions all around the world, regardless of what's melting, and this is why granites tend to have similar compositions. It's because they are limited by a phase diagram that's defined by a eutectic. Okay, so at this point, I hope that these first three concepts are pretty solid. Also, that students are able to understand binary loops. And I know I didn't talk about eutectics very much. I just wanted to introduce this concept that there is a eutectic, this minimum on a phase diagram, because if you take courses in igneous petrology, you find that eutectics are really important for understanding granites and basalts.